Hey, physics, it's Will again. I'm just going to continue. This is part two of what I had mentioned earlier. We're focusing again more about inertia, understanding the whole state of motion, um, and so on and so forth. Just to recap, inertia is all about, as it's stated here, is a natural property in which objects will typically want to either be at rest or be in motion, depending on the circumstances of all the forces that surround it. Um, so when it comes to being able to describe said object, we typically describe its state of motion in terms of velocity, which is speed with the direction. And when it comes to an object that's at rest, well, its velocity is zero, and when it's in motion, its velocity will be x or whatever it is. Let's now move on to a little bit of some practice problems here. So we're gonna. This is also an opportunity for me to test out a few of those screencast tools. Bear with me as I'm practicing trying to write and draw with a mouse. I actually ordered a graphics tablet to that should come in Thursday. That should be able to allow me to uh, write and draw very effectively. Not that I could draw very effectively in the first place. Anyway, these two problems here help help with dealing with the idea of inertia. So let's take a look at it. A group of physics teachers is taking some time off for a little putt-putt golf. The 15th hole at the hole-in-one putt-putt golf course has a large metal rim that putters must use to guide their ball towards the hole. Mr. S guides a golf ball around the metal rim. When the ball leaves the rim, which path, 1, 2, or 3, will the golf ball follow? So let's take a look at our diagram here. This circular black line is this metal rim that's being described in which the ball is traveling along. Now, we're assuming that the ball, now it's not clearly shown here, but based upon my knowledge of this situation, I'm going to mark real quickly that this right here is your starting point. So that is going to be starting point. I don't know how to type. I would like to type. Can I type? There's no typing option? Oh my god, did I really? Oh my goodness. I failed. Anyway, so that's our starting point. And if this is the case, this ball is traveling in this manner. So, knowing what we know about inertia, an object will go in the direction that it was traveling in if it was in motion, unless a force acts upon it. So, since this is a ball on the ground, a putt-putt course, think about all the forces that could be possibly acting upon it. We have not too many that we need to worry about. So, for example, oops, that was not what I wanted to click on. Here we go. So yeah, so the main thing we gotta focus on is, I had to pause the video for a second, I apologize, is understanding the ball's movement. If it's going in a circular fashion, I kind of just drew it already. Which of these three paths would make the most sense? It couldn't be one because, like I said, the direction of travel is already indicating that by the time it hits this point where there's no more railing, this ball's direction was already going this way. It can't be three because there's nothing to guide that ball to continue in this circular motion because there's no more railing. So the logical answer has to be two at this point because all the movement of this ball is now in this easterly direction, let's call it. So that should be the answer. And let's double check, make sure it is the answer. Yes, it is. And as you can see, once leaving the rim, the ball will fall in an inertial path, which is a straight line. And that's kind of a key thing. So if you want to talk about real life examples here, let's talk about rocketry. So let's talk about rocket launches. Yeah, we know that when it comes to rockets, they typically have a parabolic curve. It's not a true parabola. It's kind of more like an ellipse. So it's kind of longer at one end and more compressed on the other. So when it comes to the reasonings why, well, again, Newton's first law is still in effect here. We have inertia being a factor. So using this image here, I can just show you this. So imagine if, let's use imagine this color here is the ground. Okay, that's a nice straight line. And now we know that our rocket is doing something like this. Okay, going in this direction like that. Now you gotta keep in mind something. So as the rocket goes further away from the Earth, you still have one force really acting upon it more than any other, aside from air resistance, and that's gravity. And gravity, being the force that we know it is, has one direction. It pulls downwards, like so. And as a result, it is attempting to pull that rocket back to the center of Earth's gravity, which is the center of the planet. But as the rocket keeps going upwards, the Earth, you got to remember, is spinning. Okay, it's forever in motion, and when it spins and it's in motion, every time the rocket goes to a certain position in its trajectory, the Earth is not only just being further and further away in one direction, but it's also going further away in a different direction, X, Y directions. So you have this wonderful arch that you get from a rocket as it launches. Okay, so that's inertia in a nutshell, also in real life. So let's go to the second problem here. So let's see what we got. A 4 kilogram object is moving across a friction-free surface with a constant velocity of 2 meters per second. Which one of the following horizontal forces is necessary to maintain this state of motion? So we typically like to draw what's called a force body diagram, or sorry, excuse me, a free body diagram. So using this as another example, I'm going to draw you that. There's our object. Okay, this is 4 kilos. It's moving across a surface. Let's say the surface is purple. There we go. At a constant velocity, moving in this direction at 2 meters per second. Oh my god, I'm terrible at this. Which one of the following forces is necessary to maintain this state of motion? So what we need to worry about in a problem like this is we got to identify what's actually really happening in terms of force with this object currently. So the key word I'm going to highlight in this problem is this right here, constant. So we have this object that is not changing its speed at all. It's constantly at 2 meters per second. That means its acceleration, which is a way to measure the changes in velocity, is 0. It's not accelerating, it's not getting faster, it is not decelerating, it is maintaining a constant speed. So, because it's maintaining a constant speed, the only thing that is needed to keep this object in motion is whatever initial force there was to begin it. Because right now, and then I'm going to highlight the most important word right here, friction free. There's no friction. So we don't have to worry about the force of friction. This object is gliding perfectly. Imagine it being in space where there is no air resistance. So you got this heavy object that's in motion. What's keeping it in motion then? Time to think. Let me clear the whiteboard here. If an object is in motion, they'll stay in motion with those very same motion characteristics. It doesn't take any force to maintain that same state of motion. In fact, the presence of a force would ruin such a state of motion and cause an acceleration. So again, the key thing back in this problem, again, this is a conceptual problem. Oops. No, come back, tools. Come back. Okay. Oh, I lost my tools. That means I'm going to stop the video in a second. But just to finish this problem off, the key words again were friction-free and constant velocity. No force from friction and no acceleration or deceleration. So that means there's no extra force being involved. So here's something to think about. If you do have speed that constantly increases or constantly decreases, or it's changing, that means your object is experiencing changes in its state of motion, which means Newton's first law comes into effect, and that means there are other forces at work. So that's the end of this video. I just wanted to cover a little bit in terms of this lecture. In terms of your assignments for this, I kind of want your feedback. This is my first time actually ever doing video. And I actually kind of want your feedback in terms of what I should do better. How can I improve? If I did some things right, please let me know. Otherwise, yeah, that's pretty much it. I'll write that out as an assignment. Otherwise, good night. See you tomorrow. Hasta la vista. Bye.